here. It's a wonderful occasion. So let's start by saying a few things about how I know Jean. So back in the mid-80s, I sort of joined the tribe of people who would see each other regularly in conferences and workshops, and many of the people in that tribe are actually in this room, but Jean was one of them. So we kept seeing each other over time in various occasions, and of course I followed all of his work. Now the thing is that for most of the people in that tribe, I guess age starts to take its toll, and you can see the difference, but not with Jean. If you look at that picture and you ask, is that picture from 1980 something or is it from today? There's really no way to tell. He has stayed the same. He's had always this very fresh looking attitude, but it's probably also correlated with the fact that he is one of the calmest persons that you can see around, very even-tempered and at the same time extremely thoughtful. So there's a lot to say about the specifics of Jean's work. I think Kumar covered the ground very well. I would just emphasize that what distinguishes it is his style of work, being to the point, finding problems that are both mathematically interesting but also tell you something about real-world systems, and an excellent taste in choosing those problems. Now, many of his writings are great, but still to this day, I often send my students to read Jean's book on queuing networks, because it has everything in there, but in the simplest way possible, the way that a starting student can really understand what's going on without getting bogged down into all sorts of technicalities. Yeah, I will not comment on the typesetting of that book, but everything else in that book is absolutely perfect. So it's been a real privilege of having this ongoing relation with Jean, meeting him all the time and getting perspective about how one should think about research and life. So I'm going to talk about a topic which might not necessarily tell you so much about the next wave of what's going to happen in networks the next 10 or 20 years, maybe more of a somewhat more esoteric topic. On the other hand, it's something that Jean has done important contributions in, so therefore it kind of fits with the meeting. So it's about max weight, much studied subject, but I will try to look at it in a slightly different way. So I had a conjecture about it and kind of didn't really had some initial idea why the conjecture might be true, but couldn't really get very far. Asked quite a few good people, nobody grabbed it. And then I had a visiting student who came from Iran, from Sharif University, kind of told him the conjecture a week before he came. So he walked in 2 weeks later and said that he pretty much figured it out how to do it after some discussions. And I had told him that if that conjecture was solved, then it would have consequences on other stuff. So I told him, okay, so now you can start working on the other stuff. And he went, well, yes, I've already done it. So he's actually a really exceptional person. He's now back in Iran, but will be looking for probably postdocs, faculty positions, hope to get him in the US, depends the way things are these days, one doesn't know what will happen. All right, so what is it about? I'm going to very briefly remind people, I guess almost everyone here knows a lot about max weight. Some people know more than I do, but nevertheless, I'll just go thoroughly and define what I'm talking about. And then I'm going to embed max weight into a general class of dynamical systems that has a structural property that one can exploit, get a general result about dynamical systems, and then start to get the low-hanging fruit. And my claim will be that results on fluid limit, state space collapse, and all that, there isn't really any probability involved in there. It's just a simple consequence of a result about deterministic dynamical systems with a certain special structure under perturbations. All right, so what's the max weight policy? If you have one server, at any time it can serve one of two queues. You serve the longest queue. That's the most trivial example of the max wait policy. Generalizing a little bit, think of having a network where you have several queues that can be served. You can serve multiple queues simultaneously, but they're interference constraints, so you cannot serve all of them simultaneously. So typically you come up with a schedule that respects whatever non-interference constraints you have. So a schedule might be represented by something like that, that says server 2, serve queue number 2, serve queue number 4, and you only keep those schedules that are allowed by the interference constraints. And there's a finite set of such possible schedules. And at any point in time, you look at the state of the queues, and you're supposed to choose one of them. And what the max wait policy does is it looks at the queue vector at a certain time, and for any schedule, it looks at the so-called weight of that. So with this schedule, it would be the size of Q2 plus Q4. You compare it with the weights of the other schedules that are possible, and you choose one, and that's the max wait policy. Now, this would be the max wait policy if whenever you serve a queue and you serve the job goes away. But if you have a network, actually jobs might not disappear. Serving a job might mean that it goes to another queue. And how that happens is determined by a routing matrix. So you want to serve things with big weight, but if you send them to a queue that's also weighted, you'd also want to take that into account. So this R generally stands for a routing matrix that represents where the jobs will go, and you also take that into account in the calculation of the weights. So that's the policy, and once you have that policy, the system evolves as follows. The next queue is what was the previous queue plus whatever arrivals, that's again a vector of arrivals at the different queues at a certain time. And then you have minus I, whatever service you give. The service is your schedule, but if the queue has fewer jobs than what the schedule gives, you cannot serve more than you have. That's why you have the minimum of sigma and q. So that stuff gets subtracted, but because of the routing, other stuff gets added to the queues. So these are the dynamics. All right, so here's what my viewpoint is going to be. Of course, as everyone, most people here know, that one can think of what's happening with a fluid model. In a fluid model, we replace the arrivals by deterministic arrivals. Let's say we have arrivals at qi at a steady rate of lambda I, and the system evolves deterministically. So if you have two queues and you serve them according to serve the longest queue, what happens is you're serving one queue exclusively, so one queue goes down, but the other queue builds up because it gets arrivals, until it hits the place where the two queues are equal. And once they're equal, the max weight policy maintains that property. It serves a little bit of this, a little bit of that in a balanced way, and it keeps going down. So the deterministic dynamics have this kind of simple nature, linear segments followed by each other. Now, if we have stochastic arrivals, what's going to happen is that you have fluctuations, and probably stochastic arrivals are going to sort of follow the deterministic path, but there's going to be fluctuations around them. So we think of max weight for a stochastic system as being essentially a perturbation of a deterministic system, where the perturbation is due because of the stochastic fluctuations of the actual arrivals around its mean. So that starts making you think of traditional dynamical systems. You have a dynamical system plus perturbations on it. What can we say about the effect of those perturbations? Okay, in order to say something non-trivial, we need to exploit the properties of the fluid system. What kind of properties does it have? The drift is piecewise constant. In one region of the state space, you move it with a certain drift. Once you hit that diagonal line, you start moving with a different drift, and so on. Okay, that's probably not strong enough to get any strong conclusions. There's another property that comes in and that's useful. It's been known for some time. I've seen it in this paper of Vijay. I don't know if it goes back even earlier, but the idea is that if you start the deterministic system from two different initial conditions and you let it evolve, the distance between the trajectories does not increase with time. So that's a good property because in some sense it's a stability property that should give us something about perturbation not having too large an effect. So let's look at it a little more. What does non-expansiveness buy us? Think of a general discrete time dynamical system where the mapping F is non-expansive. So if you start from nearby points, the distance of the two trajectories does not increase with time. And look at the perturbed version of this, where you add some perturbing noise and you ask what's going to be the effect of the perturbing noise. Okay, now here's the intuition. Each time my noise is going to take me a little away by a certain amount. That little away is not going to get amplified because the system is non-expansive, but each time I'm getting an extra perturbation. And those perturbations add up, and so we can get very easily a bound of that form on the size of the perturbation. And if you're thinking any reasonable setting where those U's are stochastic or whatever, because it's a sum of absolute values, this scales in proportion with the number of steps that we have. On the other hand, if you have a trivial system, let's say it's just moving at a constant drift and you add perturbations, then it has a closed form solution. The difference between the two trajectories is going to be just the sum of the U's without absolute values. So in a trivial system, the effect of the perturbation is the sum of the disturbances. And if the disturbances are any reasonable kind of stochastic process with enough assumptions, this is going to scale like the square root of t. So it's going to be much smaller than what this was predicting. And perhaps we can exploit that. But this is true for a trivial system. Is it more generally true? That's our wish. We would like to establish, to see whether for some systems we have a property of this kind, that the effect of perturbations on a deterministic system is bounded by a constant times the sum, the sum of the signed perturbations. So essentially the term that we had there. That would be too much to hope if we have some perturbations that add up for some time and then they cancel each other. The fact that for some time they were non-zero should have an effect. So we look at the perturbations up to time t, the cumulative perturbation, but for any k bit up to time t. So this is my final time t. At some point in the past, how big was the cumulative perturbation? This is our wish, to get a result of that kind. How can we get to it? Unfortunately, just having a non-expansive system is not enough to guarantee this. The simplest counterexample is a system that moves around a circle. It's non-expansive, but if you get positive perturbations when you're up there and negative perturbations when you are down there, actually the perturbations will cancel each other, but the divergence between two trajectories would keep increasing with time. So there's a simple counterexample that non-expansiveness is not enough. So we'll probably need more properties about the max weight policy. So what we're going to exploit is that the max weight policy is essentially the subgradient flow of a nice potential function. And here's what, let me try to give the intuition of what I mean. So let's forget about boundary effects for some time. Boundary effects, I mean when a Q hits zero, it cannot go negative. Let's forget that effect. Then roughly speaking, the change in the vector of Q's is whatever is coming in. Let's pretend arrivals are deterministic, plus the effect of the service. You subtract what you served, you add where the jobs are going to. Okay, and sigma star is determined by the max weight policy by maximizing this quantity with respect to sigma. Okay, I'm throwing here this extra quantity, doesn't matter because sigma is not involved there. What's that argmax? Well, let's think of this potential function, which is this. It's the quantity that gets maximized when you try to find what service to use. So let's look at this quantity. What as a function of Q? What kind of function it is? For any sigma, it's a linear function of Q. and we're taking the maximum of several linear functions of Q over the different sigmas, and there's finitely many sigmas. So that's our potential function. What is the derivative of this function? If I look at the derivative at this point, in the vicinity of that point, my function is linear and is given by this expression according to whatever sigma I'm using. The sigma that I'm using, of course, is the maximizing one. So the derivative of this function is linear in Q. So the derivative is going to be I minus R sigma minus lambda, evaluated at the maximizing sigma. So that's, but that corresponds exactly to that expression. This is the derivative of this function. It's the derivative, it's the coefficient of Q in this expression evaluated at the maximizing sigma. Therefore, that means that the max weight dynamics basically evolve. Okay, there's a minus sign difference from when you go from here to there that causes that. So the deterministic max weight dynamics are basically the subgradient flow of this particular potential function. So that's an extra structural property that could be useful. It is a subgradient flow of a potential function which is piecewise linear with finitely many pieces. It's convex, and these are the structural properties that we're going to use. So what can we say about such systems? Let's generalize. Consider an arbitrary subgradient flow of a deterministic system, which is subgradient of something that's piecewise linear and convex with finitely many pieces. Consider an unperturbed trajectory. This is a more precise version of what this differential inclusion means. It's the integral version. That's like the derivative. The derivative at each time must be an element of f. And it's an element. F is a set because you might have ties. There might be multiple sigmas that are optimal. So you choose between them or a convex combination of them. Because the dynamics here are non-expansive, this system is well posed. You get existence, uniqueness, and so on. And let's consider now a perturbed system in which you add the perturbation and consider the perturbed dynamics. Again, it's better to put it in integral form. So u of t is the integral of the noise that you get at each time. That allows you, if you want to take mathematical tangents, it allows you to even perturb a system with Brownian motion. So u of t, the integral perturbation, is a Brownian motion, whereas this thing would be white noise that we don't necessarily like that much. So we have a perturbed and an unperturbed system, and the theorem is that given any system of this kind, there exists a constant that guarantees that the divergence between the two trajectories is bounded by the magnitude of the cumulative perturbation rather than the sum of the noises at the different times. All right. So one of the reviewers said there must be an easy Lyapunov proof or something, and you always enjoy those types of comments. We have no idea whether there's an easy proof of this. Ours runs pages and pages, and it's quite complicated. And we suspect that there's no way to get to an easy proof because the result is very delicate. If the potential function had infinitely many piecewise linear pieces, the result is not true. If you take f to be a smooth, strictly convex function, the result again is not true. So all the assumptions need to be orchestrated just right to get that to work. Let me just give you a little bit of the idea of the proof. So with the piecewise linear constant dynamics that you get from this potential flow, the state space is divided into different regions. Maybe you start in an interior, you hit a boundary, then you hit other boundaries, and you follow some kind of strange path. This is the deterministic system. Now, the deterministic dynamics, when you are, let's say, in the vicinity of that boundary, let's blow that up, it turns out that you can decompose them in two pieces. One is a drift along that boundary that we have, and another system that kind of takes you towards that dividing line, and that direction is orthogonal to the dividing line. And so this is just a constant drift. In my motivating example earlier, I said that for a constant drift, it's only the cumulative perturbations that matter. And then you have another system that works orthogonal to that, because the drifts are different. This is a hybrid system. It's not a nice and simple one, but this is a subspace of one dimension less. So what we get in the vicinity of this dividing line is a simple system plus a decoupled system that's hybrid but of lower dimension. And now that suggests that one should be able to use induction on dimension. You get a result for all systems of dimension n, and then use induction to prove the result for all systems of dimension n+1, and keep going this way. Things are not as simple. That's what happens in the vicinity of a boundary, but when you are in the vicinity of what I call a critical point would be a place here where it's not just a boundary, it's rather a point where multiple boundaries meet. Then things there become more complicated, and you need extra arguments to control how the two trajectories behave in that vicinity. All right. So it's a nice, clean, elegant setting. So it was my students, Arsalan's idea that instead of trying to study max weight, let's abstract, generalize, and get the general result, which is absolute. Yes, I've been absolutely impressed by him. So now let's go back to max weight. We have our fluid solution, which obeys the properties in the theorem that I stated, and we have a stochastic process. So how are these different? The stochastic process is perturbed from the deterministic one because arrivals are stochastic. There are some extra complications. The Q's, if they hit 0, they cannot go below. So we need to also somehow take that into account. And also the Q's evolve in discrete time, whereas my general theorem was for continuous time. So you need some extra massaging to take care of all these details here. And once you do, you get this result that applies now to the max weight policy. The distance between the stochastic system and the fluid system is bounded by the effect of the cumulative perturbation. What's the perturbation? It's the arrivals at time k minus the mean arrival, and then these get added over time. And you see how big do they get in the horizon of interest. There is an extra term, just because this one is in discrete time, that's in continuous time. When an arrival comes, it just moves you away by more or less lambda or so. So the extra terms come in to take into account the fact that we're working in discrete time. Okay, so now anyone who's been in that kind of business can probably guess that once you have this result, there's lots of low-hanging fruit. So once you have this, the proof of a fluid limit result, if you're familiar with this thing, you probably don't need to parse it because you know what it says. If you're not familiar, it's probably too many symbols to parse in real time. But basically, if you make a simple assumption that my stochastic arrival process is a reasonable one, of course, IID processes with bounded variance or whatever straightforwardly satisfy the properties of this kind, some kind of laws of large numbers, but it's much weaker than that. As long as the fluctuations in my arrival process are smaller than n. What's n? Yeah, n is the time horizon scale. In the time horizon of n, my fluctuations are less than n. Typically, for good stochastic processes, would be more like square root of n. So this is automatically small. So if this is small, you just plug it in here, and you get that this is small, and it translates into something about the scaled Q process following the fluid process as we take the limit. So the proof of the fluid limit result is one paragraph or less exercise once you have the deterministic result. So that's basically my claim that the stochastic aspects are kind of simple, even though lots of technical ingenuity has gone into that literature. It's really a simple deterministic property that's behind it. And one can then start to get more low-hanging fruit. The business that people do in this domain is to start proving state space collapse results. And instead of giving all of the kind of detail here, let me just say that if you have a system that's just marginally stable, what's going to happen, so my total service rate is equal to the total arrival rate, queues will not go up and down, but the max weight policy will still drive the two queues to be equal. So I'm going to be living somewhere on this set, and I will be fluctuating on that set. That's what the state space collapse property is, but one needs to make it kind of rigorous. Okay, so let's make an assumption about our stochastic process, that large deviations, that is the cumulative being more than the away from the expected value, large deviations have a probability that's roughly 1 over f for some function f. What's that function? Depends on what assumptions you make for your process. In the standard large deviations setting where you have finite moment generating functions, this f would be some exponential because probabilities of large deviations fall exponentially. But you might make weaker assumptions than that. So let's make a very weak assumption that the probability of a large deviation falls like 1 over n, a very weak one. Then by plugging into the deterministic result that we have, and a little bit of extra work, can show that the fluid scaling of the process with high probability stays uniformly close to this subset of the state space, which is the state space collapse property. Some history about that. Devorat and Damon had made a conjecture of this kind in their old big paper on max weight alpha and all that. With Yuan, we managed to get a proof of this, but for the case of IID bounded arrivals, and it was based on Lyapunov functions. Lyapunov functions are great, but they don't work once you go outside the independent setting. You cannot make martingale type arguments, whereas in our setting we don't need any conditions on the nature of the arrival process. It can be extremely dependent as long as it has this qualitative property that large deviations have probabilities that fall at a certain rate. That's all we need. So it seems to be a hammer that can be used in various ways. And in the large deviation setting, f would be an exponential function of n, and that gives us a result that the scaled Q process will stay close to the fluid limit for a time interval that's exponentially large in my scaling parameter n. So typical state space collapse results tell you that the two stay close over a certain time scale. With this result, we can get it over a very, very long time scale, and one can also show that this is the longest that you can have. If you go to an even larger time scale, then the two trajectories, a large deviation would happen that would take the two trajectories apart. So you can give sharp results. Okay, some extension generalizations. You can throw in weights into the different Qs. The same argument seems to work. We haven't written down all the details, but there doesn't seem to be any hole that it also applies to back pressure policies, a more generalization of max weight. The result does not quite apply if we have max weight alpha, as it's called, where you put a power of the Q vector in there instead of the Q vector. What gets destroyed here is that this cannot be expressed anymore as the subgradient of a nice piecewise linear convex function, but maybe the end result might be true with some different method. We don't know exactly what's happening there. All right, so basically in conclusion, it's here, what I presented is a nice, simple gadget. it seems to be telling an interesting property for a class of dynamical systems. So if you're just a dynamical systems person, this might be of interest. And it gives you some low-hanging fruit and elementary arguments, and who knows, results of that kind turn out to be useful in other contexts in ways that you cannot expect when you look at them, as long as they are clean. And again, that brings us back to Jean's style, to always look for something that's clean, easy to state, simple, and see what one can get from it. And so I'll close at this point, and again congratulate Jean for entering a new phase where he can be even more relaxed, but I don't know how that can happen. Thank you.
Thanks for a great talk, John. We have, I guess, plenty of time for questions in some sense, since we have a long break, so if there are any questions.
Rankin?
Yeah. Go ahead.
You said it fails with infinitely many pieces, or continue. Can you? Is it easy to describe what the counterexample looks like in that case?
No, it's as okay. So that counterexample is by Arsalan, and I read it and reread it and try to. So if you try to mimic the counterexample that I mentioned about the rotation, the things. So, but that's the rotation, you cannot express it as a subgradient of something. So he has a potential function that looks like kind of like an open book, but you add one more dimension, and that open book keeps rotating in space and all that. So just to describe the counterexample takes a few pages, and he gets that some description that's quasi-convex, and then he needs to do how to reduce quasi-convex functions to get equivalent convex ones and all that. It's difficult. Yeah.
Do you think this type of result holds for other scheduling policies, let's say like priority in Root-to-Mar network, or proportional scheduling for queuing network?
I don't, not necessarily. I haven't looked at those, but for many, well, okay, no, the type of result or the framework might not apply. They might not fall in the class of subgradient flows that we have, but that some result of that type should be true, that the divergences of the queues are limited by the cumulative fluctuations, something like that should be true. But it would be a more complicated argument, and if at some point it ends up being as complicated as the existing proofs, then you have not gained something. So for these examples, this method gives us a shortcut. For other cases, trying to work that way might not be a shortcut anymore.
Kumar, do you have
It's more a comment than anything else. The max-weight alpha part, I had tried some of these things, trying to extend my previous work. But I got stuck because some of the equations you had to look at, solutions only existed for in Sobolev spaces and things like that. Because you couldn't get things to work in the more general continuous processes and things. There was some, at that point I gave up.
Okay.
I had a brief remark actually. So it seemed to me that the pictures you showed were corresponding to suprema of linear functions, but the essential property you used was that the flow along the boundary is something you can control. So you could probably be some easy generalization where you're taking suprema of functions for which you understand the dynamics along the component parts.
Yes. But in order to get the property that the n-1 dimensional dynamics are on a subspace that's orthogonal to that, then
Yes. All right. Well, on that note, so let's take a break and thank John again.